Okay, so remember last time we did A and B, where we say that we're told to determine whether the given set, together with the specified operations of addition, uh, is also and a scalar multiplication is a vector space, and if it is not, we should list all the axioms that fails, right, or that fails to hold. So today we're gonna be doing C. You see, with C, they say that we should uh, check if V is equals to. Say we should check if V is equals to XYZ equal element of R cubed, then such that XYZ is not equal to 0 with the usual addition and scalar multiplication. So now it means that what we're going to be doing, and now we're just gonna come and say that, let's say, let me do this. Let's say that I decide now. So let me start to prove this. Remember the question, if I remember very well, the question said that, I think it said, let me see, it said that V is equal to, I think it was, V is equal to, it was X, Y, Z, which this was an element of R cubed, such that if I multiply these three, I'm not going to get 0. I think it was something like this. Can even check that. Let me see, let me try to check if I have these questions here. I think it was something like that. Yeah, they say V is equal to X, Y, Z element of R cube. Yeah, you can say with usual addition and scalar multiplication. This is C, right? So for us to prove this, we are going to come here now and we are going to say that, let's say, for me to prove this, let me just say proof. For me to prove this, first I need to check closure under addition. We agree right now. I'm going to check closure under addition. Then I come and say that if I let V be equals to, or if I let two elements, if I let V U be an element of V, start an element of V, such that V, let me put this to show that these are vectors, such that V is equals to X, Y, Z, which is an element, let me just say X1, Y1, Z2, which is an element of R cubed, right? Such that if I multiply X1, Y1, and Z1, I'm not going to get 0. You see, right? And then, and again, I say that U is equals to A, B, C, which is an element of R cubed, such that if I multiply this, I'm not going to get 0. So when I have this now, it means that I can come and add them just to check closure. You see right now, I can just come and add them. X1, Y1, Z1 plus A, B, C, which this will be equals to X1 plus A, Y1 plus B, Z1 plus C. You see, right? And then now we see that we got this. The aim here is to find that X1 plus A, Y1 plus B, Z1 plus C. When we multiply them, I was not supposed to do this here, is not equal to 0. This is what we must get. So remember, we're not restricted here. We must take this from element of R. So it means that if we can decide to say that, let me look for a counterexample, or I decide to solve this, we know that if I decide to solve this, I can have that x1 plus a is not equal to 0, y1 plus b is not equal to 0, z1. Remember last time I was doing this just to check if I could try to prove that this is true. But we say x1 will be not equal to minus a. But we're not sure about that. What if, so the question is, can we take, let's say, can I take 1 here, and then I take minus 1 here? Won't I be allowed to do that? Won't I be allowed to take 1 and minus 1? I can be allowed. You see, right? If I take 1 and minus 1, and I find that this will be like this. Remember, x is 1, right? And I find that you see that this is wrong. You see, right? So you see that I'll be allowed to take 1 this side and minus 1 that side. So it means that we must use some counter example to prove that this does not hold. You see, right? So it means that here I can come and say, by counter example, we must disprove. The easiest way is to disprove, right? So usually most of the times you should always try to disprove. If you see that disproving is not working, it means that that thing holds. So let's say I let v to be equal, so I'm gonna pick as I picked that term, 1. So I must pick something that when I multiply them I must get 0. You said I'm gonna pick 1 here, 2, 3. I'm just gonna pick anything. I'm allowed to do this. Is an element of R3, and I pick u to be minus 1, 2, 4. This is also an element of R3. So if I take v plus u, I add them, this is gonna be 1, 2, 3 plus minus 1, 2, 4, and this will be minus 1, it's 1 plus, it's 1 plus minus 1, 2 plus 2, 3 plus 4. What do I get? I'm getting 0, 4, 7. But when I take this and I multiply them, I'm getting 0. And I'm not supposed to get 0. The condition says that this must not be equal to 0. You see, right? Hence, v plus u will not be an element of v. You said even though this is in R cubed, but it's not in v. Thus, v is not a vector space. You see, right now, v is not a vector space. So now, since we say that we have proven this, that it is not a vector space, now we can try to come up with another one to see what is it that we can do, right? We have seen most of the times how we used to prove this. We can look at D. D, they say that this is the set V of all ordered triplets X, Y, Z with usual addition and what's this? The usual addition and scalar multiplication that they give us this. So now it means that if we can recall the question said that we have the set, say that we have the set V of all ordered triplets. So whenever they tell you that they have ordered triplets, you must know what they're talking about. Sometimes they won't give you this, right? You must know what we're talking about when we have ordered triplets with usual addition, and the scalar is not usual, right? They just gave us a scale. They gave us what the scalar is, which this will be kx, ky, kz. Then they say for all scalars k. You see that? So it means that for us to prove this, remember we need to check closure first, right? We're going to check closure under addition. You see, right? Then under this closure under addition, we're going to say, let's say now I let u v be an element of v, the set v. You see, right? Such that v will be equals to x, y, z, which is an element of r cubed, and I take u, which this will be equals to a, b, c, which is an element of r cubed. Then when I check this, I'm going to say this is v, it's u plus v, which this is equals to a, b, c plus x, y, z, which this will be equals to a plus x, b plus y, c plus z. And this is also some triplets. You see, right? This is also a set of all other triplets. This is also a set of all other triplets. This is also a set of triplets. So it means that is an ordered triplets. Hence, u plus v is an element of v. You see, right now? Then closure holds under addition here. Then we check closure under scalar multiplication. When we check closure under scalar multiplication, we're going to let u be some element of, I will let this be an element of v, and this b, I won't let it be any scalar, let's just let this be an element of r, right? Such that u is equal to a, b, c, which this is an element of r cubed. Then I do this. Say if I multiply this is gonna be scalar a, b, c, and we know that this, according to the definition, say that the scalar must be inside and a outside. Scalar inside, b outside, scalar inside, c outside. But by counter example here, check something. By counter example, this we can easily see. If the scalar is negative, this will disprove. It won't exist. You see right now. By counter example, let alpha be equals to -1 and b equals to, okay, let this be equals to bc. You can let it be like that, it's fine. Which this is an element of r. This is an element of. And then this times this will be equals to -1 a, b, c. So this will be equals to -1 a, -1 b, -1 c. You see right now? So now we see that hence will not be an element of V, because this won't be now an ordered triplet. You see right now? So it won't be in V. Hence, thus, scalar multiplication does not hold. And V is not a vector space. You see right now? So V won't be a vector space. So I think I think I was told to do these questions. Let me see. I was told to do these questions. Let me check them. Uh, I was told to do these questions. I was told. Let me see. It's number. I was told to do this question. Let's see it. Number 2. On number 2, we are told to. They say. They say I should. They say I should let V be a vector space. Should let V be a vector space over R. They say that if UV is an element of V, I must show that the first one, they say alpha U minus V is equal to alpha U minus alpha V, and then they say for any scalar alpha. So for me to do this, right, first, when I'm gonna do this, first I'm told that I must prove that this left hand side is equal to the right hand side, right? But if we can look at the left hand side, we see that we're given alpha U minus V. You see, right? So when I'm given this we should know that it can be written like this. First, we must write it like this. You see, right? When we write it like this, there's this thing here, which this we can talk about it later. We can say that this one, I know that it will be the inverse of V. This one is the inverse of V. I know of this. So it's just not just any inverse. There's an additive inverse. It's an additive inverse. You see, right? So I know that this one will always remain an additive inverse. So from here, I can use some distributive properties to distribute this. I can have this plus alpha minus V. So I'll send these properties to where do we find them. So this is just some distributive. This is just some distributive property of scalar multiplication over addition. Well, it's there in vector spaces, right? That's how we have to. We'll first let V be a vector space, so we can do this. We can do this. We are allowed to do so. Remember that property that says that if I'm taking a scalar and then I add two vectors, then I distribute the scalar, I'm gonna get to this. I'm using that property. So the reason why I had to change these two pluses because I don't have the property where. The reason why I had to change these two plus, I don't have the property where I'm distributing on a negative thing. You see right now. So I'm gonna do this. And then after now distributing this, we know that we also have another property that says that if I have this alpha minus that, this will be minus alpha V. I can just put the alpha inside and then take the negative outside. You see, right? So I still have something like this. So it means that from here, I can get that alpha U minus alpha V is the same as that one. So I have proven this side. And then when I come to prove B, they say that, let me see what B is. B, they say that I must prove that U plus U is equal to 2U. They say that I must prove something like this. You see right now. So for me to prove this, remember I can start anywhere. With this one, it is simple to start here. It is simple to say that I take the right hand side. Remember this is the right hand side. So the left hand side is equal to the right hand side there. I take the right hand side, which is 2U. It's simple to change this to 1 plus 1. I put a vector there. Remember, there's that property again that says that if I have two scalars, alpha plus beta, I can distribute a vector from the right, and this will give us alpha u plus beta u. You see right now? So this is the property that we're going to apply here. So it means that when I come here, I'm going to have that this will be, I can distribute now 1u plus 1u. And there's that last property that says that 1u will always be u. You see, right? If you know them by heart, you can just put them like that. So this will be u plus u. And this is the left-hand side. This implies that left-hand side is equal to right-hand side. So you can prove this anyhow you want. You see, there are many ways you can prove it. So we can just stop here.